So as you already advertised, our project is continuation not only in a color sense, but also topic-wise, because we've just seen very nice results in the Hilbert space case. So we've seen that the domain of the square root of the operator plays a very significant role, and that although not everything, but quite a lot is known, and a special role is played by sectorial operators. So you've seen this bounded and coercive form. So that means it's automatically sectorial of angle less than pi half, and things are nice, we get maximal regularity. Well, the bad news is we will look at things in Banach spaces, so that's not enough. But the good news is there is a slightly stronger concept that you will see in a minute that gets the job done. So I don't want to tease too much and pass straight to presenting our teammates. So this is Francisco Carvalho from Delft University of Technology and Maximilian Ruff from Karlsruhe. And as you might see, this is also Sascha, as Moritz already said, from Kiel. We coordinated the project together with Christian Seifert, who unfortunately cannot be here, but is passing his greetings. But as you see, there's only 2 participants. There's 4 participants on the slide. I hopefully don't have to tell you that 2 is less than 4. Okay, mathematicians are not good at counting, so maybe I should. So unfortunately, we had some very spontaneous dropouts, namely one last week. So we'll leave it to, for instance, Project Olive to showcase some of the applications of maximal regularity in Banach spaces. They will talk about the Dirichlet Laplacian on a wedge. So there you will see some of the concepts we introduce in action. And also in Project Cyan, you will see our sectoriality and our boundedness again. So it's already nice to pay attention, but you will probably meet these concepts again during the week. So without further ado, I hand over to Francisco, who will start the presentation.
So the talk will be split up into 3 parts. First, we'll talk about UMD/HT spaces. Afterwards, we'll talk about R boundedness and Fourier multipliers. And finally, we'll talk about maximal regularity. Yeah. First, we'll talk about some motivation. So if you consider a sectorial operator with spectral angle less than pi half on some Banach space, and then we consider the following initial value problem. This is similar to a problem you saw in the ISM. So here we have the non-homogeneous case, and in the ISM we have the homogeneous case. I think this was lecture 6. In the ISM we showed that there's the following solution generated by the semigroup. Yeah. What is maximal regularity? Well, I guess I don't have to tell you now, because you just had the last talk. But if f is in LP, does it follow that the terms on the left-hand side of the equation are also in LP? Yeah. And maximal regularity is useful for nonlinear problems. For example, it has applications in nonlinear problems through the use of fixed point theorems and such. Yeah. So a naive way to check about maximal regularity is if we use Duhamel's formula. Yeah, so a naive way to check this would just be to take the norms and then move the norms inside. But we see as s goes to 0, the norm of this term behaves like 1 over s. So we can, for small s, we can estimate these by which maybe you recognize this expression. By the way, is it large enough? Do you see in the back? Yeah. Which is the one-sided Hilbert transform, which is not a bounded operator in LP. So we would at least need for the Hilbert transform to preserve the LP property. And we also need a vector valued Fourier multiplier theory to generate these for when X is a Banach space. Yeah, and at least the Hilbert transform should be bounded. This is the motivation behind UMD. So now we'll talk about UMD HT spaces. First, we'll talk about martingales, which might seem a bit random at the moment. But it is, in fact, the M in UMD. Yeah. So we take a measure space, and we consider X a Banach space, and a family of sub-sigma algebras of A. And then we consider some functions, measurables with respect to the measure space. Then a sigma finite filtration is a sequence of sub-sigma algebras that are contained in each other, and they're sigma finite with respect to the measure. A family of functions is called adapted to the filtration if it's measurable with respect to the f curly fn. So fn, the filtration tells you what's measurable at each given time. And finally, a martingale with respect to the filtration is a family of adapted functions that satisfies the following conditional expectation inequality. This essentially tells you that the expectation of the future value is the present. Is an intuitive way to think about this. Yep. And now we tell you what an UMD space is, or one of the definitions. It's if for every p between 1 and infinity, there exists some constant such that this inequality holds. Here, the Fn is the martingale difference. Oh, I should say UMD stands for unconditional martingale difference. Yeah. And then this holds for all measure spaces, sigma finite measure space filtrations, finite martingales, and scalars. And now I'll tell you what a Rademacher variable is. So it's a random variable from the measure space to -1, 1 that's uniformly distributed. And the Rademacher sequence is a sequence of independent Rademacher variables. This is the Kahane-Hinchin inequality, which was done first by Hinchin for the scalar value case, and then by Kahane for the generalization for Banach space. Yeah. So we have here, notice that the difference is the LP-LQ estimate. Yeah. And then there's an equivalent definition to the UMD property, which is the randomized UMD property using Rademacher variables. And yeah, with that and this Kahane-Hinchin, you can get that the UMD property is independent of P. But the constant in it is not. Yeah. And then the Hinchin's inequality, which is an application of Kahane, is it's for a Hilbert space. You have the following estimates, and here the proof is just an application of Kahane. Go from LP to L2, and then you diagonalize it because they're independent. Maybe I can do this. We have some time. From 1 to n. Here you want to estimate L2, which is what you use, and then because they're independent and their expectation is 0 individually, this is equal to 0 if j is not k. And then the rest of the proof is just, and then you just get that if you write things out. Okay, so some examples of UMD spaces. So if you take a Hilbert space, and then we consider the inner product of two martingale differences, we use the definition of conditional expectation here, and then here we take the term that's measurable with respect to this sigma algebra outside, and then this vanishes because of the martingale definition. Both of the terms in the difference are equal to Fm, and you get 0. And then an application of Hinchin's inequality gives you the UMD property. So UMD spaces are a class of Banach spaces, which includes every Hilbert space. So every LP space here is UMD whenever X is UMD. The proof is not so complicated, but it requires a different equivalent definition of UMD space for dyadic martingales. Yeah. And then you have that UMD spaces are reflexive. And here you can prove this by using some alternative characterization of reflexivity to construct some complicated martingales. Yeah. So then you get an example of spaces that are not UMD. Yeah, so there's a Hilbert transform connection. So in the motivation, we mentioned that the Hilbert transform should be bounded. So here we recall the definition of the Hilbert transform. And then this is a very deep result that we will not prove because I don't know the proof. Yeah, so that UMD is equivalent to the Hilbert transform existing in LP and it being a bounded operator. This is also named class HT space. So 1 implies 2 was proven by Burkholder, and then there's also proved by Fifil and Peter Michel and Pot. And then the other way was proven by Bourgain. Yeah. And now we'll talk about the R-boundedness and Fourier multipliers. Oh yeah, some motivation before. So if you take an UMD space, as we mentioned in the other side of the motivation, we wanted to get a multiplier theorem, and a dyadic decomposition would be useful. Here but this only works when X is Hilbert. So we can, this will be shown later on. So if you don't follow the details now, don't worry. So we can write F like this, and then randomize it in the following way. And then by Hintgen, this would imply 2 automatically, if X is a Hilbert space. But in 3, in the general case, UMD case, we will work with this directly to prove a multiplier theorem. So now we'll define our boundedness. So we take 2 Banach spaces and a family of operators. It's called unbounded if this inequality holds, which I'll write down on the board because we'll use it later. Yeah, no one saw that. Yeah. And then the smallest constant is called the R bound, which depends on P, but we will omit this in the notation. Yeah. Oh, thank you. So R boundedness is difficult to verify directly. Because we take a family of operators. Yeah, it's not easy to verify. So if it's R-bounded, a family, then it's also uniformly bounded. Oh, this is, to prove this, you can just consider n equal 1, and then multiply the Hadamardker variable in, which has norm 1. Oh yes, this I said earlier actually. That it's independent of P, and this follows by the Kahane-Hintges inequality. If they are Hilbert spaces, then it being an R-bounded family is equivalent to it being uniformly bounded. And that, yeah, maybe I can prove this if we have some time. So I'll prove that R bounded Yeah, so then you apply Hennenfent. And then you get, here we do it for 2 directly, yeah, because it's easier. Otherwise, it wouldn't make sense to apply Hennenfent. And then you use that it's bounded. Yeah, there should be a squared here. And then you use Hennenfent again. Yeah. There should be some constant here, I think. Yeah. And then if you take the case x and y an LQ space, then our bounded is equivalent to this estimate holding. And this is also an application of Hennenfent inequality. There were a lot of applications of Hennenfent inequality. Yeah. Then some more important properties is that the sum of 2 families is also R-bounded. This just following from applying triangular inequality. And the product is also R-bounded. And this follows from applying R-boundedness twice. Then the Kahane contraction principle. Yes. So here we can consider without loss of generality beta j is equal to 1 for the proof. Otherwise, you replace xj with beta j xj. Yes, and then we split alpha into real and imaginary part. And then we want to prove the inequality if alpha j is real with just constant 1. And then to do that, we consider ek, the corners of the square, of the n-dimensional square. And then we take lambda k integers. No, sorry. Between 0 and 1. Such that their sum to n, I should write k here is between 1 and 2n. I should have said that. This sum is 1, and then alpha is equal to the sum of up to 2n of lambda k ek. And then we take the definition and then just plug this in and everything pops out. Oh, yes. So how much larger? Okay. And then you apply this representation. you move the sum outside. Mm-hmm. Mm-hmm. Yeah, alpha j, ek. No, alpha j. So ekj, the jth projection of k, and then yeah, the macro variable. And yeah, and then you just apply that this is 1. Yeah, and then we're done. Yeah, exactly. Yep. And then the last statement. So ACO stands for the absolute convex hull, and the closure in the stroke topology is what we're considering. So one can show that, which I will not do because it's a bit cumbersome. This inequality holds, and it's just a mattering of playing with the indexes. This here stands for the absolute convex hull, the convex hull. And then we consider this tau 0, which is equal to lambda t in tau, lambda less or equal than 1. Then the convex hull of tau 0 is the absolute convex hull of tau 0. And then we apply, we note that this here is exactly what you get when you apply the Kahane contraction principle to tau. So we have that tau 0. Sorry, there's a 2. Right? Yeah, and then you take, this is, yes, then you take that convex hull of this is less or equal than this, and this is equal to what we wanted in the beginning. Yeah, and the closure in the strong topology, it's just taking a limit. Yeah, and I will give the word to Max, who will speak about the multiplier theorem.
Okay, so let's continue the talk. And yeah, as already mentioned in the introduction, we want to develop a Banach space valued Fourier multiplier theory. And for this, we just define the basic notions. So we use some multiplier function m, which should be locally integrable with values in the bounded operators from x to y. And if we now have some function phi, whose Fourier support is CC infinity, then we can define this multiplier operator Tm via its action on the function phi. So Tm of phi is defined as we take the Fourier transform of phi, we multiply with this multiplier function m, and we Fourier transform back. And from this definition, we now get that Tm of phi belongs to the space of tempered distributions, which is vector valued and defined as the space of bounded operators from the Schwarz space to y. But for our application, we want to have more, not only tempered distributions, but LP functions. So our goal will be to find conditions on the multiplier function m, such that this operator Tm extends to a bounded operator from the space LP from R into X and into the space LP of R into Y. And yeah, so let's maybe first think about the scalar valued case, which is easier when X and Y are just the complex numbers. Then you might know the Michelin theorem, which gives us such conditions. So I will recall it. So in the scalar valued case, if now m is a function that is continuously differentiable apart from possible 0, and we have the following two conditions. So we have a uniform bound on m and also a uniform bound on rho times m prime of rho. Then this operator Tm extends to a bounded operator on LP for all p strictly between 1 and infinity. And our goal will be now to extend this theorem to the Banach space-valued situation, which we have above here. And this turns out to be possible, so I present the following theorem, which was proved by Lutz Weiss. So now the assumptions are x and y should now be UMD spaces, and the function m should be, again, continuously differentiable, but now with values in the bounded operators, such that we have those two conditions. Now these sets we already had in the scalar valued case, but now these sets do not only have to be bounded, but they should be R-bounded. So we require some stronger property here. Those two sets must be R-bounded, and then the operator Tm, which again is this Fourier multiplier, extends to a bounded operator on LP for all p strictly between 1 and infinity. Okay, so one might wonder if those two conditions actually are necessary. And for the second condition, it is known that this is not necessary. So this rho times m prime of rho condition is not necessary in general. But the first one is kind of necessary. So one has the following partial converse to this theorem, which is this proposition. So if x and y are now some general Banach spaces, and we have some general L1 log multiplier function such that we have the LP boundedness for some p, then this R bound of m of rho must be finite, where now rho is part of the back points of m. So what in particular is needed is that m is L infinity, but even a bit more is needed, this R boundedness of the set. So this somehow shows that this property of R boundedness indeed is something important here in this context. Okay, so now I will talk about the proof of the theorem above here, so not about the proposition below, but about the theorem. So we will we want to see how this R boundedness implies the boundedness of the Fourier multiplier. So let's start. So first step will be without loss of generality. We restrict ourselves to multiplier functions defined on the positive half line. And now we want to apply a dyadic decomposition. So we define a dyadic projection delta j to be the Fourier multiplier with this indicator function of the interval from 2 to the j until 2 to the j plus 1. And yeah, by the UMB property, this is a bounded operator on LP of Rx. So why is that? Because we have seen earlier that the UMD property is equivalent to LP boundedness of the Hilbert transform. And Hilbert transform corresponds to the multiplier for the signum function. And from the signum function, you can build the multiplier for those characteristic functions. Okay, so so let's apply this. So we can write any f in LP, which has a Fourier support in the real half line. We can write this as the sum over those dyadic projections, and this converges in LP. And it even converges unconditionally, which means we can rearrange the order of summation as we want. So this is a result by Bourgain that we will use. And from this unconditionality, it follows the following. So we have this randomizing property. So the LP norm of f is equivalent to the following LP norm, where we apply the dyadic decomposition and we introduce random signs delta epsilon j. So epsilon j are Rademacher variables defined on some probability space omega. And here we take the LP norm not only of R, but also of omega. So this is an equivalent way of writing down the LP norm. And yeah, our next step will be to show that the set Tm delta j, where j belongs to the integers, is R-bounded. Because if we have that, then the rest is not so hard anymore. So I will just show how then the rest follows if we assume that. So then we can write Tm of f. In this LP norm, we use the property, this randomization property. We introduce the random signs and the dyadic decomposition, and we also use that Tm and delta j are commuting because both are defined via multiplication in Fourier space. And now we can apply the definition of R-boundedness because we assume that this set Tm delta j to be R-bounded. We can just get rid of the operator Tm here. And we end up with this sum, which now again by property 7 is equivalent to the LP norm of F. And this then just gives the norm bound we wanted to show. So yeah, then this would end the proof, but of course we still have to show that this set here is R-bounded, which is the main part of the proof. So let's go on with that. So first thing to know, so what in particular should be R-bounded, if this set would be R-bounded, is the delta J for itself should be R-bounded for all J. And this turns out to be true, and even something more is true. So even the set P, which are the Fourier multipliers for all intervals, even this is R-bounded. So in particular from this it follows that delta J is R-bounded. So this is some result again that we will just use. And yeah, so now the next step is for some rho in this interval, we write m of rho via the fundamental theorem of calculus as m of 2 to the j plus this integral over m prime. And now we apply some change of variables to transform this integral into an integral from 0 to 1. And yeah, then we get the following. And yeah, you might already kind of notice where the two conditions for Michelin now might pop up. So here this will be roughly the m of rho, and this will be something like rho times m prime of rho. So it already looks a bit like that. So yeah, maybe I continue the proof on the blackboard. So maybe do it here. So yeah, now we have to apply this Tm to the, we have to look at this Tm delta J. Okay. Tm delta J. So what is now this? We apply this decomposition and we note that now m of 2 to the j is now a constant operator which does not depend anymore on the Fourier variable. So this is then just m of 2 to the j times delta j. And we have plus this integral. And now we, again, this terms here in front, they do not depend on the Fourier variables, so we just copy them. Prime of 2j 1 plus r. And now this depends on rho, so here we have to think about what to do. And yeah, what we get is, this is the inverse Fourier transform, we get some indicator function. Now the variable rho, we see from this should be larger than this 2 to the j, yeah, 2j 1 plus r, yes, until, and it is smaller than 2 to the j plus 1, because we apply this delta j, and yeah, f and d r, yes. And now the next step would be to estimate the R bound of that. And for that, we use the elementary properties of the R bound we had earlier, so that we have some kind of triangle inequality and we have some sub-multiplicativity. So the R bound of Tm delta j can be estimated by the R bound of 2 to the j, m of 2 to the j for j in z, yeah, times the R bound of delta j. Plus, and for the second term, we use the convexity of R bounds, so we can interpret this integral as some convex combination. So, and we have seen already that the R bound is preserved under convex combination and even in some closures with respect to the strong topology. So we can even pass to the limit. So what we then will get here is the R bound of the set 2 to the j times m prime of 2 to the j times 1 plus r, where we now have j in z and r in 0, 1. And from this indicator function, we just get the R bound and estimate this by the R bound of this P, which was introduced here above. So yeah, and now this then again can be estimated by the R bound of here we can estimate it by the R bound of M of rho for rho non-zero. This can be estimated by the R bound of P plus here now we apply the Kahan contraction principle, which told us that in such randomized sums we can make some scalar numbers just larger. So we can replace this 2 to the j even by this number here. So in fact what we can get here is the R bound of rho times M prime of rho for rho non-zero. And again here we get R bound of P. So yes, and then let's maybe continue on the slide. So yeah, this is the same in a bit less detail. So this is what one gets, and those two sets are those two R bounds are finite by the assumptions. So then we are done with this theorem. Okay, so now in the next step I will comment on how to extend this to several variables. So this was now only on the real line. And yeah, if you think about the scalar valued Michelin theorem, you might know that C1 is not enough in general, but you need higher derivatives depending on the dimension. And so it's no surprise that this will also happen here. So yeah, the proof works with dyadic cubes instead of dyadic intervals and is of course much more technical, so we will not do it, but the idea remains the same. So kind of. Yeah, now the assumption is again x and y UMD spaces, and now M we need Cn, where n now is the number of variables. And we need this R bound. Yes, now we need this in any coordinate direction, and also for this mixed ones where each part alone is of order 1. And then again the Tm extends to a bounded linear operator on Lp for all p strictly between 1 and infinity. Okay, so this finishes the part on the Fourier multipliers, and now we give some applications to the maximal regularity problem. So yeah, so let's just recall what maximal regularity is again. So let us consider some sectorial operator with spectral angle less than pi half and some LP function f. And we have a look at the Cauchy problem u prime plus au equals f with initial value 0. And now we recall the definition. So we say that A has maximal regularity of type LP if also both terms individually belong to this LP space, and we have the following norm bound. So this is called the maximal regularity because this is the highest regularity that both terms u prime and au can simultaneously have without requiring more regularity on f. Okay, so now let's talk about how to prove such things. So we will concentrate on this au term, since if we get the bound for au, we also get it for u prime by the differential equation. So as we have seen already, au of t can be written via the Duhamel formula as this integral over a times the semigroup of f of t minus sds. So this looks like a convolution, and it is a convolution if we define the convolution kernel k of t to be a times the semigroup times this indicator function. So then we get that au is the convolution of k with f. Now we just apply some Fourier transform and inverse Fourier transform. We use the connection of Fourier transform and convolution to make this a multiplication, and we see that this will be the Fourier multiplier operator with k hat, where k hat is the Fourier transform of k. So it seems to be reasonable to compute the Fourier transform of k. So let's do this. So this now is just a formal computation. So Yeah, but let's just for a moment write down the definition of the Fourier transform, and we get the following. And we see this looks like the Laplace transform of A times the semigroup evaluated at I times rho. And from semigroup theory, it is known that the Laplace transform of the semigroup gives the resolvent. So let's just apply this. And we plug in this resolvent here. So A times the resolvent at I times rho. And the nice thing is, due to the sectoriality assumptions, we know that the imaginary axis belongs to the resolvent set. So this is well defined. And we call this the multiplier function m of rho. So what in the end we should get is that maximal regularity is equivalent to LP boundedness of the convolution operator with k, which in turn is equivalent to the LP boundedness of the Fourier multiplier with the multiplier function m. Yes. Oh, yeah. Okay. Now you see it, yeah. So let's maybe comment, why is this only a formal computation? This is because, as we have already mentioned in the introduction, this function k here might behave like 1 over t at the origin. So it might not be a locally integrable function. So one needs some regularization to make all these computations here rigorous, but this can be done. And the important thing why it can be done is because, even if the function k might be not so nice, the function m always is nice due to the sectoriality bound. So we assume sectoriality of A. This means that this function m here will be uniformly bounded in the operator norm. So and this is why we will now work with the m instead of this k function. So we want to show this, that this m is a multiplier, and we have seen it is uniformly bounded due to sectoriality, but as we have seen in the Michelin theorem, we do not only need boundedness in the operator norm, but we need R-boundedness. And this leads us to the following theorem, which gives us a characterization of maximal regularity on UMD spaces. So if A is again sectorial with sectorial less than pi half on an UMD space X and P strictly between 1 and infinity, then the following two properties are equivalent. So the property of maximal regularity is equivalent to the this set, which is the m of rho defined on the previous slide being R-bounded. So the nice thing about this theorem is that it does not only give a sufficient condition for the maximal regularity, but it even is equivalence. So let's have a look at the proof. And now, as already explained, if we have the R-boundedness, we want to apply the Michelin theorem, the operator valued we had. And this had two conditions. So the first one was the R-boundedness of the set m of rho, and this is what we assume here. So this we have. And the second one is the R-boundedness of this set rho times m prime of rho. So let's compute the derivative. This we can, since this resolvent function is holomorphic by sectoriality on some sector containing the imaginary axis, so we can differentiate it. We get the following. Now we apply some resolvent calculus to rewrite this in the following way, and we see that this just is m of rho squared minus m of rho. And now again, by the triangle inequality for the R-bounds, since m of rho is supposed to be R-bounded, also this will be R-bounded. So this is the nice thing, due to this structure of this resolvent function. If we have the first condition in the Michelin theorem, we get the second one for free. And this is also why we get the equivalence, because for the other direction, you might remember we had some proposition which told us that the first condition in Michelin, which is the R-boundedness of the m function, was necessary for a p-boundedness of the Fourier multiplier. And so this can be just applied here. So this set m of rho must be R-bounded, where rho now belongs to the Lebesgue points of m. And again, since this resolvent function is holomorphic, every point on the imaginary axis will be Lebesgue point apart from possible zero. So so this set must be R-bounded. So this finishes the proof of this theorem. So let's give some extension. So we can add some further equivalences here. So the next one is the so-called asectoriality, which also turns out to be equivalent. And what does this mean? This means we have this R bound here of the resolvent, not only on the imaginary axis, but we even get it on some sector of angle stricter than pi half, so some sector which contains the imaginary axis. And another property that turns out to be equivalent is the following. So we can also relate this to the semigroup being R-bounded, now on some sector that is possibly small. And this can in turn then be related to the semigroup on the real line being R-bounded. So yeah, this is the semigroup on the real line. This should be R-bounded, but then we need a second condition. Also TA times the semigroup should be R-bounded. Yeah, for the proof of this further equivalences, I will not go too much into detail, but I will rather give some ideas how to prove that. So more or less everything relies on the convexity of R-bounds we have seen earlier already. So this reinterpreting some integral as convex combination. So the idea will always be to find some formula, representation formula via an integral, and rewrite this as a convex combination and apply convexity. So for the first direction here, so if we have the R-bound on the imaginary axis, how can we extend it to the right half plane? This can be done via the Poisson formula, which is the Poisson formula from PDE theory, which gives the solution to some Laplace equation on the half space via some integral representation formula. And this can be applied here since we have a holomorphic function. So this resolvent function is holomorphic, so we can recover its values on the right half plane via some integral on the boundary, which is the imaginary axis here. And then using that, one can obtain that the right half plane, the resolvent is bounded on R-bounded on the right half plane. And we can even then extend this to some sector using a perturbation argument based on Neumann series. So let's have a look at some further directions. So if we have this asectoriality, how do we get the boundedness on the real line of the semigroup? This is done using this functional calculus. So this is something which looks like the Cauchy integral formula, which we also had in the ISEM. So this semigroup can be written as some complex contour integral over this resolvent function. And again, the idea will be to use some clever transformation of the integral to interpret this as a convex combination, and then you get the R-bound for those two sets in a similar way. And yeah, now for the next point is if we have the R-bound of the semigroup on some sector. No, if we have it on the real line, we want it on some sector. For this, we use the power series expansion. Since we also for the semigroup, we know this gives a holomorphic function. So it has some convergent power series expansion. This can be used here to deduce that the R-bound also extends to some sector of possibly small angle. And now for the last point, if we have R-boundedness of the semigroup, how do we get back to the resolvent? This again is done using the Laplace transform, which already mentioned earlier. Some general result from semigroup theory. The resolvent can always be written as the Laplace transform of the semigroup. Again, the Laplace transform is some integral, so we can apply some convexity argument to get the R-bound. Okay, so with this, we will finish the talk. And yeah, the main references we used were this nice book by Dan Kiefer-Priss and also the Analysis in Banach Spaces book. Okay, thank you for the attention.
All right, thanks Project Red for this nice presentation. So you left enormous amount of time, so we can ask you tricky questions. Who want to be first? Ah.
So can you explain me this convexity argument for integrals?
Okay, so yeah. Oh no, this was the wrong direction. How do I go back? Like this. Okay, or maybe let's have a look at the integral. So yeah, the main thing is it's an integral of 0 to 1, and yeah, I think probably you can write the integral as some kind of Riemann sum, and then this then is some kind of convex combination, and then you have to go to some limit, but this we can do since we had this result. Where is it? No. Okay, too many slides.
No, I think it was on the
Ah. Okay, even too fast. So. Yeah. Yeah, we have this. That yeah, the R bound is preserved under closure in some operator topology.
Yeah, so first of all, thanks for your talk. I hope my question is less tricky. So you you presented two Michelin theorems. You presented the traditional one in the scalar case, and then you showed the extension of Weiss to operators that act between two UMD spaces. And you somehow explained to us that in both results you consider the same sets, but in the scalar case you just asked it to be uniformly bounded, and in the UMD case to be R-bounded. So yeah, there's of course this intermediate case where your spaces are still vector spaces, but they are Hilbert spaces. And earlier you already explained to us that in Hilbert spaces, being R-bounded means the same as being uniformly bounded. So my question now is, would you say that Weiss's result, but applied to two Hilbert spaces, is it more an easier version of Weiss's result, or would you say it's a harder version of Michelin's original result?
Okay, so I think historically this was the Hilbert space case was proven earlier, I think by Schwarz, if I'm right. So yeah, so in the Hilbert space case, as you said, you have essentially the same as in the Michelin theorem. So yeah, no, this was here. No, here. So you just replace the absolute value by the operator norm, and then this is true. So yeah, so of course this follows easily from the Weiss theorem, but I haven't had a look at the direct proof for Hilbert spaces, which I think exists. Yeah, if this is how easy this is.
Okay, I also have a question. Maybe you want to comment on, you showed us the multi-dimensional version of the multiplier theorems, but then your application, I mean, this was a Cauchy problem. It was a one-dimensional thing. So maybe you want to tell us a bit why this multi-dimensional version would also be useful in the realm of the things that you are studying.
Yeah, so this would have been useful in the part we had to omit because our our last participant dropped out. So this was some application to elliptic operators. So yeah, so maybe let's show one slide what the idea was. No, this is the wrong part. So the idea was to study maximal regularity of differential operators, which look like that, and also with coefficients, where the coefficients could even take values in operators, and we would even do it Banach space valued. And if you study such problems, then you work on such spaces, so then you will also need the multiplier theorem in several dimensions.
Thank you. Are there further questions? Well, if there are no further questions, then we think Team Red again.